Okay, so you remember orbital diagrams is another way to show where the electrons are located or probably located within an atom. And they're drawn with little lines to represent each orbitals. The P, for example, has three lines to represent the p orbital on the x-axis, the p orbital on the y-axis, and the p orbital on the z-axis. And remember, each orbital can hold 2 electrons. Okay? The n, remember, refers to the quantum number for the energy level. So n equals 1 is the first energy level, and the only sublevel is going to be the s orbitals. So that's why we only have one s. N equals 2, of course we have 2s and 2p. And so on and so forth. If you remember, the energy levels are filled from lowest energy to highest energy according to Aufbau's principle, which is why the energy arrow is pointing up, meaning lowest energy at the bottom here with 1s, all the way to the highest energy up here with 5f. So what I would like you guys to do now is to go ahead and fill in an orbital diagram for the element zinc. Go ahead and pause the video, get a piece of paper, whiteboard, something, and fill in the orbital diagram for zinc. Alright, so you should have gotten something that looks like this. Keep in mind, I draw the half arrows to make things a little less chaotic. It may look chaotic on here because my orbital lines are really small and I have a larger pen thing. Okay, so if you notice, all of the energy levels are completely filled for zinc because of the electrons it has. So here's something I really wanted to bring to your guys' attention. Zinc, the most common ion that zinc forms is actually +2, meaning that it would lose 2 valence electrons. Now, as we're looking at these, it might not make sense to you why it would lose 2 valence electrons because then it doesn't look like that we have a full shell. So one thing that I wanted to bring to your attention is that transition metals are really weird, which you already knew. But with that being said, one of the reasons they're really weird is this S and D sublevel that we have, the 4s and the 3d sublevel, are really close in energies. Okay, so what's come to realize is that the 4s sublevel is really lower than 3d if there's no electrons in 3d. So if this 3d was empty, 4s would be lower, which is why we fill the 4s sublevel first. However, as we start populating electrons into the 3d orbital, those relative energies fluctuate, and 4s is going to have slightly more energy. Okay, so and it's very slightly because these energy levels are so close. So when transition metals lose their electrons to become cations, because they are metals, they will want to lose their electrons. They generally lose their electrons from the 4s sublevel before they actually lose their electrons from the 3d sublevel. So zinc is actually going to lose those 2 electrons to form that +2 ion. And when it does that, it will be considered stable because all of the other orbitals are full. So again, transition metals tend to lose their 4s electrons before they lose their 3d electrons when they're forming cations. Another thing I want to get into with transition metals, which is another weird thing, we know that full orbitals are stable. However, transition metals would also be considered more stable, maybe not more stable than full orbitals, but half-filled orbitals are also considered stable. And so, of course, a half-filled orbital would be like 3 electrons in the p orbitals and 5 electrons in the d orbitals. Okay, and this has a lot to do with symmetry can come into play. This is pretty symmetrical. All the electrons have the same spin in their own orbitals, and so they are going to be considered stable. Here, they don't all have the same spin, but because they each have pairs of electrons that have their own spins, then it's also considered stable. And what we could also look at for stability is that half-filled orbitals will have what's called the electron exchange. They'll have more exchange numbers. Um, what they mean by electron exchange is that electrons with the same spin in degenerate orbitals, so degenerate means the same energy, they can exchange positions. For example, if we have an atom that has the valence configuration of 3d4, 4s2, and see how it's written, the 4s2 has slightly higher energy now. That element, of course, would be chromium, 4s2, and then 3d4, or 3d4, 4s2. If we write it how it's originally thought to be, such as this, the exchange number would be limited. And again, what we mean by exchange is that electrons with the same spin would exchange positions with another electron in the same spin. So that would be one exchange, that would be two exchange, that would be three exchange. And again, this would be within the same degenerate, the same energy orbital. So that's one, two, three. This one can go to here, 4, 5. This one goes to here, and then this one goes here. And of course, the electrons are actually exchanging position, and since there is no electron here, we can't exchange with that empty orbital. Okay, so I believe I said that was 6 exchanges. 1, 2, 3, 4, 5, 6. Yes. So that would be for the traditional how we would think it would be. Now, when we actually look at it, the electrons filling would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So this one has 10 electron exchanges. So again, this is for the element chromium. Okay. This is how the electrons actually fill chromium's orbitals. Is that the 4s orbital will only have one electron, and then each of the 3d orbitals will also have one electron for a total of those 6 electrons that it has um, on that fourth period. Now, the reason this is possible between the 3d and the 4s is if we look back at the orbital diagrams and refer again to how close they are in energy level, those 4s and the 3d, that's why this is possible, because they're so close in energy level. And then once we start populating that 3D, they actually kind of fluctuate. Um, chromium is more stable with these half-filled 3D than it would be like this. Okay, so the electron configuration for chromium is actually, what is it, argon is the noble gas, so we have argon, and then 3D5, and then, of course, the 4s1. Okay, so now if we look at silver, the orbital diagram of silver, go ahead and draw that one out for silver. So if you got something like this would be the normal, regular baby chem thinking of electron configuration and orbital diagrams for silver, where we would have 4s2 and 3d9. However, we now know that the orbitals that are half-filled tend to be more stable than not half-filled. Okay, so if we look at this 3D orbital right here, oops, which I forgot a few electrons, excuse me. Okay, it is almost full. And remember, this 4s and 3D, they're so close in energies, and because we've started populating the 3D orbitals, that it actually gets even closer and fluctuates a little bit. So what I'm going to go ahead and do is erase one of these electrons from the 4s orbital, because it's not going to stay in that 4s orbital. It needs to go ahead, it recognizes that we should fill in that 3D orbital. I'm going to fix this electron that I partially erased. Oh, maybe not. Okay, so now we have this 3D orbital is full, which is more stable than how it was before. Now this 4s um, electron or orbital is not full, however, it is half full. So that in itself would also make it a little bit more stable than where it was 4s being full and the 3D having the 9 electrons. Okay. Now, if you remember, silver, oh, that was ugly, excuse me. Silver, the ion of silver will always have a +1 charge. And the reason that is because of the orbital filling of silver, this 4s electron that's going to have a little bit higher energy is going to be the one to be lost. Okay, and when it loses that one electron, it is going to be stable. And so that's why silver will form a +1 charge. Looking at copper, copper is right next to zinc on the periodic table. So it would normally be 4s2 and then 3d9. Similar to, oh, I just realized for silver, that shouldn't have been 3D. We should have gone all the way up to 5s and 4d. Excuse me for that. So this should have been 4d, and this would have been 5s. My apologies. Because copper is the one that's in 4s and 3d. Now, just like silver, it's not actually going to be 4s2, 3d9, where we only have 9 electrons here. So that one 4s electron is actually going to drop into the 3D orbitals so that we have the full 3D sublevel and only one electron in the 4s. So it would actually be 4s1 and 3d10. So for the most part, again, the transition metals are really weird, and it almost has to be looked at as an atom by atom basis for stability. But this, especially on the first row of the transition metals, those 3D transition metals, this generally um, takes place, especially with the chromium and the coppers, doing the half-filled and the filled orbitals. For the most part, this is a pretty good rule, I guess, for the transition metals to follow. But again, it can fluctuate depending on which atoms you're talking about for it. But for the most part, generally, this is acceptable rule for transition metals, electron arrangement, as well as transition metals becoming ions and losing those electrons to become cations.